Okay guys, in 9.4 we're going to look at some tests that compare one series to another. And this is very useful when we have a series that kind of looks like something that we're used to but not quite, and we can compare it to something more familiar. So for example, this series right here, the 1 over 2 to the n plus 1, it kind of reminds us of the series of 1 over 2 to the n. It kind of looks like that except for this plus 1 part. All right, and why is that helpful? Well, we know that 1 over 2 to the n is a geometric series. And then, so we can rewrite that as 1 over 2 to the n power, if that helps you. So that means that the r is equal to 1/2. And so we know that this series is convergence. So let's compare this term by term. So for the 1 over 2 to the n plus 1, I've got terms 1 over 3 plus 1 over 5 plus 1 over 9 plus 1 over 17, and so on. And then for the 1 over 2 to the n power, I've got 1/2 plus 1/4 plus 1/8 plus 1/16. So you can see term by term that our original series of 1 over 2 to the n plus 1 is always less than 1 over 2 to the n power. Okay, so we can conclude then if these terms are always smaller than the 1 over 2 to the n, then our original series converges just like the 1 over 2 to the n power. This is called the comparison test. Okay, so suppose we have two series. We've got a to the n, and then we've got b to the n. Okay, and they have positive terms. So if b to the n is convergent, so b to the n is like the familiar one. So this one, the green one, is the familiar one, and we know it's convergent. So if we know that the one that we're trying to figure out, if those terms are always less than the terms of the one that is more familiar, then the original one, will also be convergent. So think about that. If I've got something that's getting smaller and smaller, closer and closer to some value, and I have the other values that are always less than that, then that will also be converging to some value. Maybe not the same value, but it will be converging to a value. Likewise, if I've got my familiar series is divergent, then I want my actual series that I'm comparing, I want that to be greater than b to the n. Okay, so if that's true, then my a to the n is also divergent. So let's think about that. If I've got some values that are diverging, so that would be like my b, my familiar series, all right, and these terms are always greater, then won't those also diverge? So that's what we're saying in the comparison test. All right, so two types of series that we usually use are things that are easy to compare to. So we've got the p series, which we talked about in class. And remember, if p is greater than 1, it converges, and then if p is less than 1, it diverges. And then we also had the geometric series from the previous class. And remember that if we said r is less than 1, then it converges. And then if it was greater than 1, then it diverged. Okay, so let's do some examples. So we're going to look at this series, and we want to determine whether it converges or diverges. All right, so if we look at this, there's a lot going on here in the denominator. But what's driving this series is this highest power, 2 to the n squared. So let's compare that. Let's see what do we know about a series that's kind of similar to that, which would be the series 5 over 2n squared. Notice that I kept the numerator the same and I kept the coefficient the same, but all I did was I dropped these tailing terms. Okay, so if you notice that the original series, so this is like my AN, this is like my BN. My AN, 5 over 2 to the n squared plus 4n plus 3. These values always are going to have a larger number in the denominator. So here, denominator is bigger than the BN, which is just 5 over 2 to the n squared. Okay, so it's bigger than that one. So that must mean that our overall value, this makes the one on the left smaller than the one on the right. All right, so let's look at this 5 over 2 to the n. I'm going to rearrange that so that I'm going to pull out the 5 halves. Remember, we can take out a constant out of a summation, all right, out of a series. And then I've got 1 over n squared. So this is simply just a p series where my p is equal to 2. So since p is greater than 1, then we know that this is going to be converging. All right, so since my AN is less than BN, and because BN converges, then my AN also converges by the comparison test. Moving on. So we're going to look at this next series, natural log of n over n. Again, I want to pick something that is very familiar to us. And the thing about ln, that's the part in the numerator. So let's compare it to something that has something different in the numerator but the same denominator. Okay, so we've got 1 over n. The reason I'm going to pick 1 is because I'm going to compare, I can easily compare natural log compared to 1. Notice that the denominator will stay the same. Okay, so what do we know about natural log and 1? Well, after we get, say, e, natural log is always going to be greater than 1. So after a certain point, so after how many terms that we have to do in order to get to ln greater than 1, then we're going to have our ln of n is going to be greater than 1 over n. And I'm going to put after so many terms. I believe it's for n is greater than or equal to 3. Oh, I forgot my n there. Okay, so check me on that. Make sure it's 3. All right, but after 3 terms, then that ln of n over n is greater than 1 over n. And what do we know about 1 over n? 1 over n is that harmonic series that we said was divergence. So that must mean, since here's my AN, here's my BN, since A of n is larger than B of n and B of n is diverging, then A of n is also diverging. And we would just say by comparison test. Okay, so that's the direct comparison test. We're directly comparing one series to another. Now, if we get something, if you read this little paragraph, the terms being tested must be smaller than those of a convergence series, or those terms being tested must be larger than those of a divergence series. If you have terms that are larger than a convergence series, or if you have terms that are smaller than a divergence series, then the comparison test doesn't apply. So you can't make the opposite assumption. All right, so if that happens to you, you need to try a different test. So let me show you another test. This is the limit comparison test. So again, it's a comparison test because I'm going to be looking at an original series versus another series that is more familiar or that is closely related to that original series. So this is saying if I can take the limit of the rate, I'm going to be taking the limit of those two series divided with each other. And if I get some number L, then they either both converge or they both diverge. So that's where it's important to pick our Bn carefully because we want to know whether that one diverges or converges. All right, so if we do this series, notice this is very similar to the one we started with, except I have 1 over 2 to the n minus 1. If I compare 1 over 2 to the n minus 1 to 1 over 2 to the n, notice that these denominators will always be smaller than that one. So I'm actually going to have the original series larger than 1 over 2 to the n. Well, we know that 2 to the n is convergence. So the direct comparison test doesn't really help us. So we can't use comparison test. So instead, we're going to do a ratio, the limit of the ratio of those two. So I'm going to do the limit as n approaches infinity of my original one, 1 over 2 to the n minus 1, over 1 over 2 to the n. Now notice these are very similarly related, and I still know that 1 over 2 to the n is converging. I'm just doing a ratio of those two in the limit of them. Now, if I rewrite this a little bit, this is going to be the limit as n approaches infinity of 2 to the n over 2 to the n minus 1. Now, one of our techniques, remember, is we're going to divide by the highest power in the denominator. So I'm going to be dividing everything by 2 to the n. Look at what that does. Now, we haven't really done that with power, but it works just the same as it does with polynomials. All right, so I'm going to get the limit of 1 over 1 minus 1 over 2 to the n. So if I do the limit as n approaches infinity, this part right here is going to go to 0, and then I'm just left with 1. So again, this is my L. That's my number that it needs to, as long as I get some number, then I know both of these are going to do the same thing. Both of these series are going to do the same thing. So since 1 over 2 to the n converges, we know that I better put my summation. Then we know that the series 1 over 2 to the n minus 1 also converges. And we know that by the limit comparison test. Okay, so make sure to read the top of page 627. That has basically it's showing you that the limit comparison test is really good for those messy kinds of series, and we can compare it to the P series. So they give you some good examples and a good strategy for doing that. So we've got 2 more tests that we can use in order to determine whether a series converges or diverges.